Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be doing a brief discussion of magnetic field flux. So in the past, we've had definitions for vector fields and vector field flux. You'll recall that for fields in general, the flux of a general vector field is defined algebraically as the vector field dotted with an area vector. So V is any vector field, A is area of a surface for which the flux is defined. And recall that the area vector is always perpendicular to the surface which it is the area for. So that is the definition in general. We did, for example, the flux of an E field, which was E dot A. This led to Gauss's law for what it's worth. Today we want to do the flux of a magnetic field. So flux of a magnetic field would be B dot A. So just as this leads to Gauss's law, this other one will lead to a law as well. I'm going to just leave it as a blank for now, because that's for another video and I don't want to kind of like jump ahead on it. But I will discuss this law in another video along with the name. It's a name that you're all familiar with. In fact, it's the same person who gave us the concept of electric field lines and of vector fields in general. So, moving on. What does this mean? Well, let's say that I happen to have a surface, maybe given by this right here. It has some area A. So area A, the area vector would basically point up out of the surface like this. It's perpendicular to the surface. Now we add in a vector field, specifically in this case, a magnetic field. So maybe the magnetic field is incident like this on our surface. It's actually kind of, make note of the fact that it's basically doing like this, and then so on. Okay, so here's my magnetic field, which is uniform B, and if I kind of blow up the B vector is like this, the A vector in this case is like this. So this is equivalent to saying that the area vector is here and the magnetic field vector is down here. So this is A, this is B, and the angle is always counterclockwise from first to second. So from B to A, if we're doing this dot product. So here's the angle phi. The flux for the B field is again B dot A, which is equal to the magnitude of B times the magnitude of A times the cosine of the angle phi. This gives us the total flux for the magnetic field, and the unit that goes with it is the Weber. So if this is magnetic field flux phi B, unit or MKS unit for phi B is Weber, which is equivalent to 1 Tesla times a meter squared. All right, So from there, really, we have to make a couple of notes. One of them is that in Gauss's law, so Gauss's law for E fields, you basically ended up getting that the sum of E dot A for a closed surface was equal to Q enclosed, the amount of charge enclosed, over epsilon naught. So flux through a closed, that would be therefore three-dimensional surface's surface. In the case of magnetic fields, what you get is this. Gauss's law for B field is that the same basic idea, B dot A for a closed surface is equal to 0. And the implication of this is that there are no magnetic monopoles. So that's just our Gauss's law equivalent. Second item is basically what happens if you want to just look through a flat surface. So these basically are use flat surface to get non-zero flux for B field. And so in that case, you end up with this equation that we have right here. And so I'll just kind of copy it over here instead of having to rewrite the whole thing. Maybe. So that's that. Quick example, and then we'll wrap up. A uniform magnetic field of strength 1.2 teslas is incident on a piece of paper which is 20 by 30 centimeters. It's incident at an angle of 30 degrees with respect to the surface, so what's the flux? Basically, if I was to draw the paper from the side, here's the area vector, and then the magnetic field basically is sort of incident like this on that paper. And so this angle right here has been specified as 30 degrees, which makes this angle right here 60 degrees. So putting all that together, you get a flux phi B of B times A times cosine phi, and that is B times length times width times cosine phi. So phi is 90 minus 30 degrees, or 60 degrees. This is your width, this is your length, this is your B. So the flux phi B would therefore be equal to 1.2 Tesla times 0.2 meters times 0.3 meters times cosine of 60 degrees. So that is a total flux phi B of about 0.036 Webers. So that's all that I'm going to do in today's video. I hope you've learned something about flux from today, and thanks for watching.